welcome Tim McKay for today's department colloquium. As a reminder, students and postdocs are invited to meet with Tim after the colloquium in PSB 403. I understand there's pizza. So Tim is the Arthur F. Thurnow Professor of Physics, Astronomy, and Education at the University of Michigan. An astrophysicist by training, Professor McKay has turned his expertise as a data scientist to educational data and data about students and teaching and learning. I think his work is a wonderful example of taking a physicist's approach to physics education research, answering questions such as developing and studying digital learning tools and coaches, exploring the vast amounts of student data that we collect at institutions, and understanding how to curate and share those data with students or faculty or for research purposes. Today he'll be telling us about a national collaboration that he has been leading, SEISMIC. So please join me in welcoming Professor McKay.
Thank you very much. It's a real pleasure to get a chance to come here to Cornell and to share some of this work that's been going on over the last couple of years. I like to start with a slide like this because this is really what this is all about, right? It's about training people and launching their lives. We play a really key role in doing that, and I want to make sure that when we do that, we do it in a way which is really informed by evidence and is thinking really hard about whether it is providing the equal kinds of opportunities to all students that we would like to provide. So let me begin with a little bit of background just to frame the work that I'm going to describe. So as Natasha said, I am a person who has always been drawn to projects that have rich data and diverse goals. I love to ask and answer questions using data, so I have done that originally in projects of astrophysics, like the Sloan Digital Sky Survey, which made the first really large map of the universe in a digital form, the Robotic Optical Transient Search Experiment, the Dark Energy Survey. These are all big astrophysical survey projects. They have one important relationship to educational data that I want to mention, which is that when you do cosmology projects, you do observational science. You don't get to do experiments in cosmology. And so you think a lot about how to draw inference from observational data. And I find that very often in education work, we also find ourselves trying to draw inference from complex observational data. Another feature of this work that was important for what we'll talk about today is that I've always worked in big and multidisciplinary teams in order to accomplish these projects. And I think that we're going to need to work in this kind of multidisciplinary team to establish the data that we need and to do the experiments we need in order to answer these big questions. So the reason that I've turned to doing education research in recent years is really driven by a mix of interest and opportunity. It is the case that today there are rich and extensive sets of data about learners and the contexts that they're in, so we can see what they're doing and what's happening with them in a way that didn't exist when I started teaching at the University of Michigan in 1995. And I think that this data provides an opportunity to change the way we do STEM education, to make it much more equitable and inclusive. There are many aspects of this, many parts of the education system that we might want to think about working on. My primary focus for the last few years has been on large foundational courses. This is both because I teach those courses and I really want to work on making them be much more successful. We use these large courses as laboratories for exploring teaching and learning. I think if we're going to teach 700 students, we should be learning something about the process of teaching and learning in the course of doing that. And I also work in these spaces in practice. I really want to design and deliver courses that will promote equity and inclusion while being also extremely effective. Now, it's unusual maybe to think about equity and inclusion as design goals for this kind of work. So why is it that I think we should focus on equity and inclusion? This is a conclusion that has come to me and others across the national scene in recent years, in part because of our recent history. So we've been trying to motivate efforts to really transform foundational STEM courses by using good evidence for overall learning gains for years. Right? There has been increasingly good evidence that more active forms of learning can lead to better learning outcomes for students. That evidence has been present for decades, and yet most of the classes around the country have still not changed. This leads me to believe that this evidence is an inadequate motivator for people to change. It's just not enough by itself. So, there are real and persistent problems with equity and inclusion that I think can provide a very different motivation for action. And I have seen in my own work that this motivation for action can get an unprecedented amount of commitment from people who might work on this problem. There are many people who, if I tell them completely changing their teaching might lead to a 10% improvement in student learning, they won't have the time to do anything about it. But if I can show them that in their learning environment there's a real problem with equity, that will get them to do something about it. So using this as the central motivator is enabling us to get commitment from students, from faculty, and from administrators. And the basic idea is that, improving average learning is a nice goal. It's a good thing to improve average learning. But creating a learning experience which is equitable and inclusive is a moral obligation. It's a different kind of thing. So that's why we've tried to place equity and inclusion at the center of what we're doing. This is the kind of teaching environment I usually work in. It's actually not quite as big a room as this, but sort of similar. I'm the blurry person at the front of the room with a couple of demos, And I used to think, when I was teaching these classes, that providing every student with exactly the same environment was equitable, that was equity, that was fairness, right? And I now really believe that the opposite almost is true. If we don't attend and respond to difference in our students, then we're just not being equitable. We really have to account for the fact that not all of our students are the same. We will simply replicate inequities that are brought to us when we do that work. So let me give you a bit of the history of how we got to the point where we're doing this work. The place where this work started for me was in examining my own course. This is Physics 140, Introductory Mechanics for engineers and physical scientists. About 700 students. They meet in 3 groups of 240 or so in this large lecture hall environment. We started to probe equity in our own classes in around the year 2010 using what we describe as grade anomalies. So in order to understand student performance, we wanted to learn from experience, and so we looked back at past classes and examined what things we knew about students at the beginning of the class that were related to their performance at the outcome of the class, right? Because we wanted to be able to measure not just did students do well or poorly, but how did they do in comparison to what you might expect? Did they do better than expected or worse than expected, right? So we wanted to make that kind of refinement. And what we discovered is something everyone in the education world already knew, that if you want to predict a student's grade in a class, you should look at their grades in other classes, because the strongest predictor is that, right? Not standardized test scores or anything else, but grades in other classes. So we will be making a comparison of GPA in other college courses, what I'll call GPAO and some of these things. To first order, grades predict grades. And that is kind of almost independent of discipline. It reflects a variety of studenting skills. So why do we use this GPAO as a predictor? First of all, students think of themselves to some extent in this way. You might even remember yourself as a 3.8 student. Or a student might come up and say, I'm a 3.2 student. It's like an identity factor almost. They think of themselves this way. And so students that get grades that are lower than what they usually get are perceived as penalties or failures on their part, right? Wherever they may be referencing it, the relative grade is relevant for students. So that's one reason why we think about this. We defined then a grade anomaly, which for any student in a particular class, the grade anomaly is very simply just the grade in this course compared to their grade in all the other courses that they've taken. And in this work, we learned 2 key lessons. The first lesson that we learn is displayed in this figure. So first of all, let me explain it. This is a student's grade in their other classes. This is their grade in this Physics 140 class that I just showed you a picture of. What's shown here are a set of points down the middle. Each point is the mean and the error on the mean, the uncertainty of the mean. For students who came in with this particular GPA, they receive a grade that looks like this. The dashed lines represent the 1 sigma dispersion around the mean for individual students in that, right? So the means are very well determined because there's 24,000 students in this figure. We teach physics to a lot of students, all right? So what do you see when you look at this figure? You can see, of course, that students who get high grades in other courses also tend to get higher grades in physics. But if you look a little bit closely, you will notice that almost all these points are below a 1-to-1 line. If students received grades in physics that were equal to the grades they received in other classes, they would be on that line, of course, and they're all below it. If you average that grade anomaly for all of the students in this class, average this quantity of grade minus GPO, you get the average grade anomaly, which for this class is about -0.5 a letter grade. So students sign up for the physics class, their GPA is going down on average. It's not their fault, right? In fact, I can prove to you that the students who take physics actually generally perform better in their classes than other students on campus. But when they come here, we give them lower grades. That's just a choice that we kind of make. So there are substantial grade penalties imposed by physics, and it turns out this is true for all large introductory STEM lecture courses on our campus, probably on your campus too. It's a kind of disciplinary norm that's present mostly across the country. So that's one thing we learned. The second thing we did when we started to look at this data is we asked a few questions about equity. Once you have this kind of information, you can start to ask what might be affecting student performance. And so here's an example of what you might call an equity analysis, where you take two different groups of people and compare their relative performance. So here we might have students in one lecture, about 14,000 students in that group, students in this other group, about 5,800 students. And when we look at this figure, we might see that students in one of these sections had one kind of performance, and in another they had another kind of performance. The average grade anomaly for these two groups is different, very significantly different. Well, you can see it yourself there. 0.3 letter grades, 0.6 letter grades. So the performance gap between these two groups of students is about 0.27 letter grades. If you saw this, would it raise equity concerns for you? Would you worry about that, right? I mean, you'd have to ask lots of questions. You might want to ask, are the students the same in these two sections, right? You might want to study that and see. Maybe there really is a difference in the students. But you have to ask yourself, would it, one of the ways in which we might traditionally look for equity concerns in classes is if a class is taught in many sections, even lab sections probably here, someone checks to see that the average grade in those lab sections is not wildly different. Because they have a sense that they should be fairly similar, and if they are different, there could at least be an equity concern, right? So I think seeing a thing like this would make you wonder whether there was an equity problem here. You would want to think about what other factors might be involved in the differences among these students. So in thinking about performance and equity, there are a variety of factors that might seem valid predictors of performance. So some factors that have a more or less valid, or maybe you could say fair or equitable relation to performance. If you knew, for example, that the students in one of those sections spent 3 hours a week more working than the students in the other, and had good evidence that that was the case, then okay, maybe it would be fine, right? Maybe it would be equitable. If you could see that the students had very different performance in other places, you might think that that was adequate. If you could see that the students had much more prior training in the subject or different standardized test scores, whatever standardized test scores might mean, these are all things that might feel like explanations for this. On the other hand, there are a variety of things that you might find out about the students that would seem like they were invalid explanations for this difference in performance. And that could include like the chance assignment to the instructor. If you give two large groups of students, two different instructors, and one group of students does much worse than the other, that feels kind of inequitable. That's like not fair for the students, right? If the room or the time of the class meeting was responsible for this, that would also be troublesome. You would want to work against that. And if it was true that the difference between these students was gender or first-gen status or national origin or income, that would also feel like an invalid explanation for this. It would create a problem of equity. And the reason that I like to go through this kind of discussion is because that original figure that I just showed you actually isn't lecture 1 and lecture 2. It's actually a figure that compares male and female performance in that class. Okay, so here it is again. Differences in grade penalty by gender in this course provided us with what I think are clear evidence of equity problems in these classes. We put students into these classes, they have similar background and preparation, and I will tell you we've done everything we can to try and explain away these differences without being able to do that. They come out with different performance. The environment we've created creates these problems of performance. I think it's on us to do something about correcting them. So my first lesson that I want to give to you about this is that data can provide insight into questions of equity. We all knew this all along. We would use data to make basic checks of what's going on in our classes, right? That's what we're doing here, making basic checks of what's going on in the classes and finding things that look like equity problems. I will also say that analyses like these can lead to lots of problems and confusion of various kinds. So for example, when I first discovered this about my own course in physics, I started talking to my colleagues at Michigan about it, and my colleagues in chemistry started telling their students not to take physics from us because we were clearly biased against women. Which was not a completely crazy thing for them to do, but it was also kind of irresponsible because they should have asked a different question. Is it just physics or not? And I have to say, I'm embarrassed that I did not immediately ask that question myself, because I should have. Right? It's an obvious question. So we went through a period of 1.5 years or something when that kind of thing was happening. It can create problems, it can create confusion. it certainly, if nothing else, means that you have some kind of obligation to think about it or try to do something about it. To ignore it is not really acceptable. Okay, so what is it? Is it a problem with physics, or is it not? So eventually, we got to the point where we were able to do this kind of examination for all of the courses on our campus. We focused mostly on large courses, but we can do it for all the courses that are on our campus, and what we found is that it is not only in physics. Here's another example of gendered performance differences in an introductory econ lecture course, Econ 101, Microeconomics. Same kind of thing, very similar kinds of performance gaps, slightly different, but very similar in structure, male students and female students. We then continued to examine this across our whole campus, and I'm going to show you now a figure that represents both the overall grade penalty of the class on the x-axis, so courses that give out relatively high average grades on one side, relatively low on the other, and then the gender performance difference on the y-axis for a whole set of large introductory science and math courses. So here's that figure. This is all courses at Michigan. Average grade anomaly for the whole class on the x-axis, higher mean grades on the right, lower mean grades on the left. Gender performance difference on the y-axis with a 0 set up here where the dashed line is. Okay. Courses above that line are courses where female students generally outperform male students. Courses below that line where male students generally outperform female students. Now, you don't know all the course numbers of all of our classes at Michigan, but I can tell you this is every large introductory course in physics, chemistry, biology, mathematics. And if you look at the pattern that you see on here, you'll notice there are two colors of points. There are blue and gray points up here. These are points that go to lab courses, and the red points are all lecture courses. So what we saw when we looked at this is a large group of STEM lab courses that give out slightly higher grades than students receive in other courses, but are generally gender normed, similar performance for male and female students. All of the introductory STEM lecture courses lie in a circle over here on the lower left, which give out both low mean grades and have large gendered performance differences. So it's not just a problem in physics. In fact, if you look down here, you will find our general chemistry class. These are the same people who were telling their students not to take physics because it was biased against women. All right? So it's not a problem of physics. It's a problem that has something to do with the structure and environment of these large introductory science lecture courses. It's not a science problem either. It is, of course, true that what we do in lab and what we do in lecture is quite different in a bunch of ways. In some ways, what we do in lab is more authentic than what we do in lecture classes. Just let me say, since I became a professor, no one has ever sat me down to solve problems on a multiple choice test. It is not a part of the function of physics to do that. It's not very authentic to do that. What we do in lab is at least a little bit closer to that. People are asked to think about something, write it up, much more like what we do in the real world. So this is an artificial environment that seems to be creating these kinds of problems. All right. None of the prior performance information we have explains these gender performance differences, so we've used everything from high school, all the standardized tests. We've used it in a variety of models, hierarchical linear models. We've also done matching models that don't require linearity. We've done everything we can to try and make this go away, because I don't really like believing that I've created an environment that does this. But it doesn't go away. It's a real effect. All right. I think they represent strong evidence of what lawyers call disparate impact. I don't know how many of you know about the law of real estate discrimination, but if you want to prove discrimination in real estate, you don't have to catch someone saying, I'll never rent an apartment to a person like you. You just have to show that they never do. Showing disparate impact is cause of action in certain kinds of legal situations. I can imagine that our students might someday decide that they should sue us. I'm not suggesting that they should. But I think they might have a claim that there's something so wrong here, and we've known about it and we've done not that much about it yet. So. Okay, so is this just a problem at Michigan? This was the next question that came up. And this is a place where the work that Natasha described about trying to help people get their data together to be able to do this kind of work has consumed many years of my recent life. Martha Pollack, before she became your president, was our provost. And she invited me to come to a meeting of all of the Big Ten provosts. And the Big Ten being the Big Ten, there were 14 of those provosts. So I went into this room. I was supposed to tell them about the work we've been doing on learning analytics. And here's 14 provosts sitting around the table. They all get to sit in the front row, you can imagine, right? Because they're provosts. If you get the chance to speak to a bunch of provosts, I suggest you tell them what they should do, because they might do it. And if provosts want to do something, they can just do it. Right? They're provosts. So what I told them is, here's what we're seeing. We should really share our data and make this comparison. And it was fun to watch because they all kind of looked around at each other, like, oh, okay, yeah, you're right, we should do that. There were two exceptions because at the Big Ten Academic Alliance, there are two private universities that are involved, the University of Chicago and Northwestern, and they were like, yeah, that's a great idea. Go do that. It was an interesting experience. So we started a project to try and do the same kind of analysis on multiple campuses. And it was the longest 2 days of my life, the first meeting we have, because all these people have been brought together to do this comparison, and I told them what we were supposed to do, and they said, no, we're not going to do that. Right? So it really was a long process, difficult to do. We did, in the end, manage to do a project that was called the Sloan Learning and Research Analytics Project. The Sloan Foundation gave us a little money to support that project. And the results of that were reported in a paper that Rebecca Matz from Michigan State University published late in 2017 about patterns of gendered performance difference in large introductory courses at 5 research universities. So although we had brought 10 people to the table, we were able to get 5 of them to actually do the analysis and be willing to talk about it. And here's one of the figures from that paper. I'll just focus on the chemistry example. So general chemistry labs and big general chemistry lectures are in these 2 circles. And I like to call out this particular example because it is in physics, for one thing. But mostly because general chemistry is the first course of science that so many students take. So they come to campus, they take general chemistry, and what happens? First of all, everyone is given a grade that's really quite low. The grade anomalies are like 0.7 letter grades. And then, female students in that class pay an additional quarter letter grade kind of price. So welcome to science. You're not as good at this as you are at everything else you're doing on campus, right? Okay, so these are some points about data and